Welcome to Pre-Calculus. Today we will investigate solving polynomial inequalities about box volume, focusing on efficient strategies for solving for reasonable widths, lengths, and heights. Let's take a look at one example. Our scenario here is that Italy is putting together flower boxes. The length of the boxes she's making must be 4 less than the width, and the height must be 6 more than the width. The volume of the box must be less than or equal to 24. And I've got a coordinate plane here, so if I look at my instructions, one of the first tasks I want to do is I want to write a function to represent the box volume and graph it along with the maximum volume line. And then from that graph, we'll determine the interval of possible width values, and we'll record it using interval notation. Well, let's focus on that first task of writing a function to represent the box volume. So I'm going to pick up my pen and I'm going to go directly to the words where I have length, width, and height described in terms of their relationships to each other. So the first connection relationship I see is that the length must be 4 less than the width. I also have a second relationship here. The height must be 6 more than the width. Now, in terms of the dimensions of the box, I have 3 essential dimensions. The first is the length. Second is the height. And the third is the width. And just to keep in mind about what we're trying to describe, it's a box that we could put flowers into. So I'm just going to make a rough sketch here. We'll call this the width. And the length is smaller than the width, so I'm going to make that a little smaller. So that would be like our lid. And then the height is greater, 6 more than the width. So I'm going to call this the height. And that gives us an idea about what we're trying to describe. It's a box, some kind of rectangular prism that's a real life type application. I could put flowers in that box. What we need to decide is how to label algebraically the length, the height, and the width. So the way that we start with that is we just want to see in the description, what is the common comparison? So I see length is compared to width, as is height. Height is compared to width. Now, when I see a repeated dimension like that, that is the one that I'm going to label with my single variable. So that's going to be represented by x. And again, I choose that one because it's the common comparison between 2 other ones, the length's comparing with width, the height's comparing with width. And what that lets me do is now write expressions for length and height in terms of the width, which I'm representing as x. So to return to this length, the length must be 4 less than the width. That algebraically I could describe as x, the width, minus 4, 4 less than the width. Notice with that description of length, I do put minus 4 after x. A lot of times we look at this word than as a word that switches the order within a sentence. So even though it's saying 4 less, than switches it so that the width or x comes first. Same for the height. The height, I'm told here, is 6 more than the width. So again, I take the width. I've got that word than, the switch word. So I put the width first, and then 6 more I'd represent as plus 6. Now I want to put that together, and I need to think about geometrically how would I come up with the volume of that box knowing the length, the height, and the width. So remember from geometry, the volume of that box would be equal to the product of the width times the length times the height. So that's how I want to set up my function. So it's going to be, we can call it v of x or f of x. We'll call it v of x since it's about volume, and it's depending on the length of these 3 dimensions, length, height, and width. So v of x equals, so I'm just going to use my little rule over here from geometry. The width I'm calling x. The length is represented by x minus 4. And then the height is given as x plus 6. And that is a function that would represent the volume. So I'm going to box that. Now I want to graph that, but I also want to think about the constraints of the situation. Really, our maximum volume that we're told this box can have is 24. And what this implies is that I really have an inequality that I'm going to use my original function for volume and this number 24, because the volume must be less than or equal to 24. So we'll graph the function separately, but what we're really trying to ask is, where is this function for the volume, so x times x minus 4 times x plus 6, less than or equal to 24? That is the inequality really that we're trying to solve. So I will say this, we'll go ahead and put this line here just to say what's the maximum volume, and that we'll call we'll call it v sub max is going to be 24. And I put that as a small separate equation because what we'll do is we'll solve our inequality using those two equations, the one in the green, the one in the blue. So I do want to graph those. I'm going to record them, and then I'm going to go over to Desmos to take a look at the graph so we can put it here on our coordinate plane. So let's head over to the graphing calculator. And again, what we want really is a table of values that will help us recreate the graph on our screen. So first thing, I'm going to type in v of x, that's my volume function, equals x, I'm going to type it in its factored form, times x minus 4 times x plus 6. Again, that's the width times the length times the height. And I see right away that I've got kind of my graph going off the screen. So I can just hit the zoom out button, or if I want, because I see my x dimensions pretty good there, it's capturing most of the graph, I can just adjust the y. So you just kind of make a guess. I'm going to say negative 15. That's not quite enough, so let's go negative 25. We're getting there, but still I don't see that lower piece, so let's go negative 40. And that gives us a good view of that lower part of the graph. And then let's catch the upper part by changing the maximum part of our y-axis. Let's go 50, almost 75, and there we go. So that'll work for us. So that's the function for our volume. Let's go ahead and get a table for that so that we can graph it on ours. So at negative 2, the volume is given as 48, negative 1, 25, 0 is going through the origin at 0, 1, negative 21, 2, negative 32. And I see that I really don't have any points to the right or to the left, so I need to include some more x values. So let's get our left values here first. Let's try negative 3 and negative 4. And notice that catches that relative maximum on the far left. So I'm going to include negative 3, negative 4, and I'll put those as 63 and then 64. I do also want to grab the actual maximum. So on Desmos, remember you just hover over that place and click to get the actual x and y coordinate of the max over there. That's negative 3.573 and then 65.671. And you can see why it didn't make it into our table. It's an irrational number. I also need some values on the far right side so that I catch that relative minimum. So there's 3. We could even go to 4 and we can see there's a 0 there. So 3 has the output of negative 27, 4 has the output of 0. And then I also want to catch the relative minimum. So if I click there, you can see again, it's an irrational number, 2.239. negative 32.485. Now, the only other piece that I need is what would give us an inequality. So we have that our maximum volume, which we had called V sub max, I'm just going to call it Y, could have been 24. And I'm going to graph that line because I want to see where on my graph is that hitting, so that I can interpret the situation. So what I need to do here is I need to grab some intersection points, and then we'll put them on our own graph when we get there. So I'm going to zoom in a little bit. And it looks like there on the left, we have an intersection of the maximum volume 24 and negative 0.96. And I'll zoom back out. And I want to find this intersection on the right. So that's at 4.507, comma 24. Did have a far left intersection at negative 5.54724. So I'm picking those out because that's the critical points there, the intersection values. And what I'm going to do now is I'm going to take this information and head back to the notes, and then we'll try to answer the questions once we have this graphed. So what we'll do is we'll create some space here and make our table here on the left. So again, this is for the actual volume function. We're trying to recreate that cubic function. So we had picked up these x values, negative 4, negative 3, negative 2, negative 1, 0, 0, 1, 2, 3, and 4. And the outputs we had gotten, just to remind again, because we'd seen these once on the graph, so this is our volume function, v of x, is negative 4 is 64, negative 3 is 63, negative 2 is 48, negative 1 is 25, 0, 0, 1, negative 21, 2, negative 32, 3, negative 27, and 4 is 0. And I left spots here to put the relative maximum, so that's at negative 3.573, and that's at the high value of 65.671. You can see that's bigger than its neighbors, so it's definitely a maximum. And then our relative minimum was here between 2 and 3, so at 2.239, it had the small value of negative 32.485. So let's graph that. I'm going to pick up my red here. So negative 4 is at 64. So on my graph, I see the scale is by 5. So I have to estimate here. So negative 4, negative 64. Negative 3.573 is at 65. And then negative 3 itself is sitting right next to it at positive 63. Negative 1 is at 25. 0, 0. 1, negative 21. 2, negative 32. So notice I'm just making estimates, but they're reasonable estimates. The minimum is at 2.239, negative 32.48. So not far from that point we just graphed. And 3 is at negative 27. 4 is at 0. So that gives me enough to graph. It is a slimmer graph based on this scale here that we've got on our coordinate plane. So it hits that maximum and then rebounds back to the origin and then hits the minimum and then rebounds vertically to positive infinity. So there's our volume function. And what we want to do is bring also that line that we'd graphed through 24. So I'm just finding these y values at 24, plot those, and then let's sketch our maximum volume function. So that's the Vmax. Now, what's left for us to do is determine the interval of possible width values and record using interval notation. So I'm going to focus on this inequality, and really we want to use this graph that we've made with the red volume and the green maximum volume line to interpret what's our solution for this inequality. So what I'm looking at just algebraically is we're saying, where is this inequality on the left less than or equal to this value 24 on the right? So if I were to highlight those places on the graph, it's anywhere where the red volume function is below that green line. So algebraically, we would describe the intervals that contain those really two parts of our volume function, the two parts that are below the y value of 24. But we also need to think in terms of the scenario, what x and y values would be reasonable given that we're talking about lengths and volumes of boxes. So just to kind of think about our domain and our range, our domain here, if I'm thinking that it's connected to widths, lengths, and heights, has to be only part of our x real line. It can't include the negative values because, again, distance can't be negative. It must be either 0 or positive. So we're looking at x values that are greater than or equal to 0. So in terms of just saying, okay, out of those highlighted parts, which ones have x values that are 0 or greater, that's this right-hand side, now in green. So notice we had to limit it down to that right-hand piece based on our real-life scenario constraints. Let's also think about the range. So the range, the y values in this real-life function would have to do with volume. And again, we need to think about, in terms of real life, what types of numbers could describe volume for us. Can we include negative volumes? And when we ask that, we really don't include negative volumes. That's not something we see on an everyday basis. So again, our y values would also be restricted to being 0 or above. And so if I highlight a third time, I'm really now looking at this small piece that I'm highlighting in blue. So notice it fulfills our two constraints on our domain and our range. The x values are positive and the y values are positive. So all I need to do now is decide, okay, over what x values is this one piece that we highlighted in blue, where does it exist? So that helps probably to bring back that intersection we had found on Desmos. So that intersection on the right is the point 4.507, comma 24. And really I'm just describing, if I think about that place on the x-axis where it has the y value 0, that from our table we can see is the x value of 4. 4 has the value of 0. So to answer the question that really is the so what of this problem, what's the interval of possible width values? It's really from 4, again, we're looking at these x values, that's my width, up to 4.507. And that's how I'm going to record this. And since we are including the equal option, the way I'll say possible width values is that it would be bracket from 4 up to 4.507. And I'm including the brackets there because I'm saying that it could equal 4 if I wanted the volume to be 0. The width could equal 4.507 if I wanted the volume to be exactly 24. If I put it with parentheses, I would be saying that those are the x values, but I would exclude 4 itself, which probably is smart because usually volume is not 0. We don't want a 0 volume flower box. Or the volume's not equal to 24. It comes up to maybe 23.99999, but not 24. So let's highlight our final value here. Thank you for joining for this investigation of solving polynomial inequalities using some graphical strategies and reasonable interpretations of the graph to match the inequalities we've produced algebraically with a real life scenario with all of its constraints. I'll let you go work on your own polynomial inequalities. See you soon.